Good morning, Doctor. We are Group 8, and today we will be presenting our project on modeling the spread of infectious disease using epidemiological and dynamical system analysis. Our presentation will having 6 contents. Our model is a modified epidemiological SIRV model, which used to study how disease spread in population, which includes 4, which is susceptible S, infected I, recover R, and vaccinated V. The model is epidemiological because it tracks disease dynamic over time using biological meaningful parameters, which is infection rate, recovery rate, vaccination rate, and immunity loss. It is modified to include birth, deaths, vaccination, and different life stage and warning immunity, which making it more realistic for long-time disease control. This is the dynamic of the SIRV epidemic model. Note that n is constant total population size which dn/dt equals to 0. And we substitute all the equation inside and we prove that n equals to 1. For the statistics of the system, we are using the reduced SIRV model which substitute dv/dt into the ds/dt, dt, and dr/dt. Then to find the equilibrium point, we let ds/dt, didt, and dr/dt equals to 0. At first, we use I equals to 0, which means it is a disease-free equilibrium to find the equilibrium point E0. Then we use I not larger than 0, which means it is an endemic equilibrium EE to find the E naught. For the E0, there is no infected population which the susceptible population S is maintained along with vaccinated individuals. And for the E naught, given that I naught is larger than 0, so we call them a endemic equilibrium. Now we are doing our analysis for the statistic by doing Jacobian matrix. First, we define F, G, and H to solve the Jacobian matrix of equilibrium. Then we substitute the E0 into the Jacobian matrix. Then we will find that there got 3 eigenvalues for the E0. Given d, theta, pi, nu, gamma are larger than 0 and the alpha and sigma is between 0 and 1, we note that the lambda 1 and lambda 3 are always negative. Hence, lambda 1 and lambda 3 are stable. Then for the lambda 2, there are 2 cases, which case 1, when lambda 2 is larger than 0, lambda 2 is positive, then lambda 2 is unstable. For the case 2, lambda 2 are less than 0, which lambda 2 is negative, then lambda 2 is stable. By getting the 2 cases above, we get the reproduction equation, which is R0. When R0 is larger than 1, the DFE is unstable saddle, while when R0 is lesser than 1, the DFE is a stable node. Now we will move on to find the statistic of the endemic equilibrium by using Jacobian matrix. Since there is too many unknown and too complicated, we decided to substitute the value of constant variable inside the equation to find our lambda. By using the MATLAB tool, we will compute the eigenvalues for EE. We can easily to know that the lambda 2 is always negative. However, it is too complicated for us to find the stability for the lambda 1 and lambda 3. Hence, we decided to visualize the graph for these 3 eigenvalues using the versus I. This is a graph for lambda 2, which we use the manipulator value for the pi, sigma, and I. And we know that the lambda 2 is always negative, hence it follows that lambda 2 is stable. Lambda 3 is always negative, hence it follows that lambda 3 is stable. For the graph for lambda 1, we know that there got 2 cases with lambda 1 larger than 0 and lambda 1 lower than 0. Hence, we can conclude that when the R0 is larger than 1, the DFE is stable while the EE is unstable. And when the R0 is lesser than 1, the DFE is unstable and the EE is stable. Now I will pass to my teammate for the next.
Good day, everyone. My name is Joyce. In this part of the presentation, I walk you through the dynamic of the SIRV model using both time series plots and phase portraits. We analyze how different combinations of vaccination rate and vaccine efficacy affects the stability of the disease-free equilibrium and endemic equilibrium. The disease-free equilibrium, or DFE, refers to the state where no infection persists in the population over time. The behavior around this equilibrium depends heavily on the eigenvalue lambda 2. If lambda 2 is greater than 0, the equilibrium is unstable and infection tends to grow. If lambda 2 is less than 0, it is stable and infection dies out. Let's now explore how this plays out under different scenarios. For the first scenario, both the vaccination rate and efficacy are low, leading to an unstable equilibrium. The susceptible population starts high but decreases slowly. Infected individuals grow steadily due to lambda 2 is greater than 0. Recoveries gradually increase as people heal. Vaccinated numbers grow slightly but not enough to make an impact due to low vaccination and low vaccine efficacy. And this shows us how effective control can lead to sustained and worsening the outbreaks. And for the face portrait, the infection curve is more open and spread out. This means the infection and recovery stages last long, the peak number of infected is higher, and the outbreak is more prolonged. It visually supports the idea of an uncontrolled growing epidemic. So for the epidemiological interpretation, this unstable scenario represents a real-world situation with low intervention and high randomness. It may occur due to virus mutation, poor vaccine coverage, or behavioral factors like frequent movement. The result is an outbreak that may never fully go away, cycling through the population repeatedly. So for the second scenario, although the vaccination is still low, the vaccine itself is effective, and thus the susceptible decline slowly, the infected rise slightly, and then decrease over time as lambda 2 is less than 0. The recovered individuals increase and then slightly decline due to loss of immunity. The vaccinated group slowly grows and plateaus. So even with the low vaccination, but the high efficacy helps to suppress the disease. So for the face portrait, it shows a sharp peak of infection, followed by a steady decline. It is a classic epidemic wave where the infections start small, rise sharply, and then fade. The recovery follows the same cycle, and this system settles into a stable pattern. So for the epidemiological interpretation for the second scenario, it reflects low randomness and low control. But due to the vaccine efficacy, the outbreak naturally dies out. It doesn't require large-scale intervention, resembling historical outbreaks that fade once herd immunity is reached. And now we explore the third scenario with a high vaccination rate but with a weak vaccine. The susceptible drops initially, but then rebound due to immunity loss. Infected individuals experience repeated waves. The recovery increase, but can't fully suppress infection. Vaccination is widespread, but the weak efficacy and fast waning lead to only temporary protection. So now let's look at the face portrait. The infection curve here is gentle and prolonged, where there is no sharp peak. The infection doesn't drop quickly, and the loop continues, suggesting recurring outbreaks. This shows us that even strong interventions fail if the tools are weak. So for the epidemiological interpretation, this is an unstable system despite high control. It mirrors that real-world scenarios like the flu or COVID-19, where the disease keep coming back due to mutation or behavior changes. So without booster shots or improved vaccines, the outbreaks are likely to recur. So finally, we have both high vaccine coverage and strong vaccine protection. We can see from the graph, the susceptibles drop rapidly, the infected individuals decline sharply where its potential to be zero, the recoveries rise slightly and level off. The vaccinated population grows quickly and stabilizes. And we can see that this is the ideal case for disease elimination. And for the face portrait, this curve flattens quickly, indicating that a rapid resolution of the outbreak, very few people get infected or recover. The disease fades before spreading widely, and this is a successful containment strategy in action. So as we can see from the graph, these stable systems show high control and low randomness. It suggests an efficient public health response, effective vaccines, and minimal external disruptions. The disease is well managed and doesn't spread widely. So let's move on to the MATLAB coding for disease-free equilibrium. So this is our code. Then okay, that's the end of disease-free equilibrium. That's all from me. Thank you.
Hi, I'm Panisha and now I would like to present about endemic equilibrium. So first, we assume the vaccination rate V equal to 0.05 and the vaccine inefficacy sigma equal to 0.04, which means we have low vaccination and high vaccine effectiveness. In this case, we found that the endemic equilibrium is stable. We can see that susceptible begins from a slightly negative point and increases gradually toward a small positive value when the vaccinated proportion decreases. Then the infected people in endemic is always will not be non people, so it starts above zero and starts to decline steadily toward zero after receiving a strong vaccine. We can see that the susceptible proportion is higher than the infected proportion around day 20 onwards. In this case, the recovered proportion declines slowly. To continue control the outbreak, the vaccinated proportion will increase steadily and near to 1, which is the constant total population size. This indicates that although the vaccination is in progress, the residual susceptibility still remains, possibly indicating waning immunity or stochastic return to susceptibility. From this first portrait, we can note that it is a stable dynamics. Negative eigenvalues indicate that the endemic equilibrium is stable. The outbreak is controlled, so the infections will die out over time. Although the vaccination rate is low, but the system still stabilizes due to the outbreak can be controlled by a strong vaccine. And now we have low vaccination and also low vaccine effectiveness. In this case, we found that the endemic equilibrium is unstable. When the vaccinated proportion falls down, the susceptible slowly increases, means some individuals may become susceptible again, while the infected increases and peak around day 120 and then become stable after day 120. This indicates a persistent outbreak and reaching an endemic state. The vaccinated decreases may due to waning or demographic turnover. In this case, more people recover over time, but outbreaks still remain. So the first portrait is unstable in this case because of the low vaccination rate and weak vaccine failed to suppress transmission. This will cause the outbreak expands with the rising infected, as a weak vaccine can compensate for slow rollout, thus the outbreak persists. Next, however, if both vaccination rate and vaccine effectiveness are high, from the graph that the vaccinated increases steadily and approaches to 1 after day 100, means nearly whole population received the vaccine. Due to the strong vaccination control, susceptible and infections decreases and stabilize near zero, then recover proportion rises initially and then becomes stable indicates that a small group of people recovers before outbreak is halted. Therefore, the endemic equilibrium is very stable and reaches disease-free equilibrium with a strong vaccination control. When both vaccination rate and vaccine effectiveness are high, the endemic equilibrium is stable. This means that with a strong vaccine and high vaccination, the endemic can be well controlled and the fast path decays approaching to zero infection. This first portrait shows the best control system compared to others for the endemic equilibrium. Lastly, we have high vaccination and low vaccine effectiveness. In this case, susceptible increase and then stable, while the infected also increases and it is persistent at a moderate level, which is an endemic scenario. Vaccinated declines over time due to waning immunity, although the recovery level increases, but it is not enough to end the outbreak. Therefore, the endemic equilibrium is unstable and it will be a long-term endemic. So the trajectory in this fast portrait shows the graph of infected and susceptible proportion, although it's a high control in vaccination rate, but due to the high vaccine inefficacy rate, the disease persists. Hence, the endemic equilibrium is unstable despite interventions. In conclusion, a high vaccine efficacy rate is very important for controlling the disease outbreak. The higher the vaccine efficacy, the better the outbreak control. So next will be the mallet code that we have generated to visualize our time series and fast portrait. Alright, so this is the mallet code for the time series. Then, then, and then this for the fast portrait. Then, alright, so that's all for me. Next, I will pass to Wenjing. Thank you.
My name is Lee Wenjun, and now I'm going to talking about the epidemiological analysis. So this is a SP part text, and the initial fee is 0.05 and sigma is 0.04, and we will change it according to different cases. For first one, when phi equal to 0.05, and we change it to 0.2, and the sigma is equal to 0.04. From this bifurcation diagram, the population of S decreases, and it shows no interesting impact on S. Second, the bifurcation of diagram for V is increasing when the phi changes from 0.05 to 0.2, and we fix the sigma equal to 0.04, and it also shows no interesting impact on V except the smooth increasing. Next, the bifurcation diagram for infected population when sigma changes from 0.04 to 0.2. From this diagram, the population keeps decreasing until the threshold value 0.11. Then the population increases and suddenly jumps to a value of approximately 280. So it shows that the infection will persist in the population if the vaccine effectiveness is lower than 0.089. However, from the backward, the effectiveness of vaccine must be greater than 0.911, which is the threshold value of 0.089. The effort is greater than from the forward. So it is known as the backward bifurcation, or also known as subcritical bifurcation. Okay, so for the bifurcation diagram for V is also similar. So when the threshold value is equal to 0.11, after that the vaccinated population will drop. Okay, and the effectiveness of the vaccine must be greater than 0.911 so that the lower stable branch can jump back to a high stable one, and also it's a backward bifurcation. Next, the bifurcation diagram for S when phi changes from 0.05 to 0.2 and fix the sigma equal to 0.2. So from this bifurcation diagram, the position of S decreases and no interesting impact. Next, the bifurcation diagram for V when phi equal to 0.05 to 0.2 and sigma equal to 0.2. So from this bifurcation diagram, the position of V also increases smoothly when the value of V increases. Okay, so for bifurcation diagram for I, which is infected population with phi equal to 0.2 and the sigma changes from 0.04 to 0.2. From this bifurcation diagram, the infected population will keep decreasing until the threshold value of 0.1166. So then the population of I will increase smoothly after the threshold value, and the infection will persist in the population if the vaccine effectiveness is lower than 0.8834. And also for each sigma value, we only have one and only one stable equilibrium, unlike the backward bifurcation. So this is known as forward bifurcation. Next, the bifurcation diagram for V when phi equal to 0.2 and we change the value of sigma. Okay, so similarly, while the diagram is opposite, so the vaccinated population will keep decreasing until the threshold value of 0.1166, and the population of V decreases smoothly after the threshold value, and is known as forward bifurcation. Conclusion. So for our system, it exhibits both DFE and EE, and this aligns with phenomena of backward bifurcation. And we also shows that the vaccination is not always sufficient alone. The immunity also matters in our models, and the initial conditions also matters because it will converge to an endemic state even with intervention measures if we choose the incorrect initial conditions. And also, we use a time series simulation to validate the theoretically steady states and local stability analysis. We also shows that with the bifurcation diagram illustrate how the increase in the vaccine efficiency, which is sigma, it will lead a transition from DFE to EE. Next, we also show some diagram like time series and bifurcation diagram, and we also provide the threshold criteria for each of them. And we also show what if simulation to evaluate how different the vaccination strategies or efficiency level affect the long-term outcome. And we can turn this mathematical result into some practical advice, like recommending stronger vaccination campaigns, better quality vaccines, or just adjusting the booster schedule to the policymakers. And for the control efforts from the government must enforce high vaccination coverage, especially for newborns. And government should invest in the development and distribution of high effective vaccine to minimize the vaccine inefficiency. And also, they should keep tracking for the threshold and determine whether the system is at risk of shifting to an endemic equilibrium. For the NGO, they can help to educate the public about the importance of vaccines, fighting the misinformation, and reaching out to remote or underserved communities. And for the health clinics and hospital, they can detect and report cases early so that we could collect the accurate data to update the models. So that's all from us. Thank you so much.